Photoelectron Spectroscopy 1.6 PES. Looking here at our picture before we begin. Similar to the mass spectroscopy, where you're using the spectrometer, you have a source that's firing photons at your sample, and it's emitting electrons. And those electrons, and they're in a higher energy state, so they go into this machine, and then the detector picks up their energy signature, their energy excited amount, and it graphs it, basically. And you get these little peaks and things. So that's the kind of basic idea of what's going on in terms of the machine. But we're going to get into all the nitty-gritty here, so you have to be able to read these graphs, these photoelectron spectrographs. Learning targets. Explain the relationship between the photoelectron spectrum of an atom or ion and the electron configuration of the species. So from the graph, you need to be able to identify an electron configuration. Also be able to determine the interactions between the electrons and the nucleus. So this is where some of that, like Coulomb's law stuff, is going to be applied here with the ionization energy. Basically using the photoelectric effect. Einstein was the one that came up with the photoelectric effect, showing that you give energy to electrons. You give them enough energy, because remember, it has to be that quantized energy amount, has to reach that quantized packet of energy in order to emit the electron. And then you can look at its configuration after you know those energies from the machine measuring it. Briefly reviewing the photoelectric effect from Einstein. Einstein made the observation that many metals emit electrons when light shines upon them, just regular light. Now, in order to get some of these atoms to do this, they have to give them higher energy photons. So you saw the UV and other ones on there as possible ways of getting them to emit electrons. When photons collide with the electrons, energy is transferred from the light to the electrons, and then the electrons, of course, are freed from the atom. They emit. They overcome the attractive force, and they are emitted or released from the atom. The electrons that are emitted are called photoelectrons because they're in an excited state. They have more energy. How does it work? Substance is bombarded with photons. Like I said, UV, it could be regular light depending upon how high energy those electrons are. They showed you some of the other sources. There was X-ray, I think, on there. So any of the photon from the electromagnetic spectrum that has high enough energy to emit electrons can be used. It's going to be relational to a given amount of energy based off of the frequency or the wavelength. We're not going to do the calculating with these equations just yet, but remember the energy of the photon equals Planck's constant times the frequency. So you could use the frequency of the photon to figure out how much energy has been given to the electron. Or if you're given the wavelength, you could still substitute in from the speed of light equation the wavelength. Combine the two together, so Planck's constant times the speed of light over the wavelength would also give you the energy of the photon. That would need to be equivalent to the what the electron would absorb in order to be released or emit from the atom. We're not going to do these calculations and stuff at this point. Those are going to be saved for Unit 3. Photons are absorbed, electrons are emitted. Basically what's going on here. So you see these are the photons going in. The electrons now absorb that energy and then they emit or eject from the atom. Now in order for it to emit, it has to be equal to or greater than the ionization energy. Remember, the ionization energy is equivalent basically to the force of attraction holding the positives of the nucleus to the electron, that Coulombic attraction. So you have to overcome that Coulombic attraction, and it's a certain amount of energy in order to do that. Ionization energy, a measure of the coulombic force of attraction between the nucleus and the electron. It's also referred to as binding energy because it's like the force that's holding those two together. You have to overcome that force in order to get the electron to be released. So it's an amount of energy. The binding energy and ionization energy are the same magnitude number. One is referring to like the attractive force, this coulombic force. The ionization energy is the energy needed to remove. So they're really referencing the same point here. Must overcome, the ionization energy must be overcome in order to emit the electron. The higher the ionization energy, that means it's a stronger force, obviously. You need more energy to overcome the force. So what does a graph look like? It looks like this, with these funny little peaks on it. So what does this photoelectron spectroscopy data show us? Shows us the relative number of electrons on the y-axis. So look over here on the y, you see the relative number of electrons label. These peaks are giving us the relative number of electrons. On the x, we see the energy, and it could be called ionization energy, it could be called binding energy, and a lot of times it just says energy. This is the spectrograph for nitrogen, by the way. Okay, so we're looking here at this spectrograph for nitrogen and these peaks for nitrogen. Now, pay attention to the x-axis for this energy. See, we have 100 over here to the left, we have 0.1 over here to the right. The higher the binding energy or ionization energy right here, this is going to be the side that's closer to the nucleus because it has the stronger force. So the one that's closest to the higher energy side is always going to be the 1s. That's going to be the first energy level because that one's the closest to the nucleus. So of course it's going to experience the highest force of attraction. All electrons in the same sublevel have the same ionization energies, kind of. Now I say kind of because if you look at the graph here, there's this little part in between where there is a little bit difference between some of the electrons in the 2p and in the 2s and in the 1s, but relatively they're basically the same amount. One peak for each sublevel. So the 1s has a peak, the 2s has a peak, the 2p has a peak. The peak height corresponds to the relative number of electrons. So if you look here, and this is nitrogen, and we know nitrogen has 7 electrons, and we know the configuration, if we look at the periodic table, is 1s2, 2s2, 2p3. If I look at the periodic table, I can figure that out. So when I'm interpreting this graph, I'm looking at the relative heights here. So that means the 1s is 2 bars here represents 1 electron each. The 2s can hold 2 as well, so 2 bars on this graph equal 1 electron each. So if I look at the 2p then, how many bars do I have? I have 3. So I have 3 electrons in that height of that relative peak. And that does correspond to what my configuration for nitrogen would look like. So let's take a look at lithium here. I want you to pay attention to the x-axis on the lithium because look what they did. They put the higher binding energy over here on this side to the right now. So this is the higher side. Sometimes they reverse them. So you have to really pay attention to that x-axis. Which side has the higher energy? This one's lower. So the one that has the higher energy is closer to the nucleus. That one's got to be the 1s. Now the relative peak size, if we're looking at this example, you could see here, it doesn't have those bars like the previous graph, but if we look at the relative heights here, this one looks about half of this one. That's why this is labeled 2, this is labeled 1. This is about double the size of this peak. Well, if we know, if you look up lithium on the periodic table, lithium is 1s2, 2s1. So that would make sense that the 2s over here with the lower binding energy would only have the height half of the 1s. So there'd be 2 electrons in this one electron in this peak. So the peak for the 1s is bigger because there are 2 electrons. The peak for the 2s is at a lower energy, so this 0.52, because it's easier to remove from the 2s because it's a farther distance from the nucleus in terms of the Coulombic attraction. So let's look at this one example before we go. First thing I should do is look at that x-axis, determine which side is my higher energy, the right or the left. Which one's the higher energy? The right. So guess what that peak over there to the right is going to be? Here is my higher energy. So this peak, the first peak, the closest to the higher energy, that's my 1s. That's where I start. The next peak over must be the what then? The 2s, good. And this tall peak, it's got to be the what? 2p, very good. Then comes, what's next? 3s. And last but not least over here, this small one is going to be the 3p. And if I look at their relative heights, this amount of electrons in this one, this would be 1 electron, this would be 1 electron. So that would be 1s2, 2s2, same height here, 2s2. If you could see, 1, 2, 3, 4, 5, 6 in my relative height, this is going to be 2p6. 1, 2, 3s2, and then the 3p over here only has 1 electron in it. Then I look at my periodic table, 3p1, which element am I talking about? Or what's the square of which element? Yes, 3p1 here, looking at aluminum, that's 3p1. And I have identified my element based off of the graph and can write the configuration based off of the graph. Looking here at exercise 1, taking a look here. This is a photoelectron spectra of an unknown element. That's what we're going to start with looking at. We need to determine the electron configuration and the identity of the element here. Anybody have any idea where we need to start? What should I look at first? Remember, on the y is the relative number of electrons. The x, we have the energy. Now, what did we say is important about the energy? Yes, energy is important, but what do we need to look at first about our energy here? Where do we need to start in our graph? The higher energy or the lower energy? So yeah, we look over here at the higher energy. That's the one that's going to be the closest to the nucleus because it's experiencing the most attractive force from the protons in the nucleus, this electron. So the higher energy side, remembering from last time, is going to be the closest orbital to the nucleus. So what is our closest orbital to the nucleus? What am I going to label this one? This is the 1s, good. So that means the next peak over is going to be the what? The 2s, good. And then this one, of course, comes after the 2s is the 2p. Very, very good. All right, now, after we figure out which orbitals are which, now we look at the peaks. So I'd start with the peaks second. This peak right here compared to this peak, and compared to this peak, they're relatively in terms of their height. So if this is saying this is 2 electrons, this one's 2 electrons, and this is about half of it, that means there's 1 electron. Now sometimes they label the peaks for you, like in this graph where it's saying this has 2, and that one has 1. Some graphs it does not, so you have to look at the relative height to determine the number of electrons. So this would be 1s2, because there's 2 electrons in the 1s. This would be 2s2, there's 2 electrons in here, and this would be 2p1. So 1s2, 2s2, 2p1. That's my configuration, so that's what I need for this part. Now, to identify the element, what should I do? Yes, I need the periodic table. Very good. So I'm going to go ahead to my periodic table, and it was 2p1, 1s2, 2s2, 2p1. So which element are we talking about? Here is your 2p row. Yes, we've got boron here because this is the p1 of the 2p row. So boron would be our element from that particular graph. We look at our configuration and then we use our configuration to identify the element. So this would be our boron would be this particular graph here. Looking at exercise 2, they give you a different kind of stacked graph. It looks a little bit different. So, but you still follow the same general rule as we did in exercise 1. So you tell me, where am I going to find my 1s? Which peak is my 1s? Is it in the top part of the graph up here, or is it the bottom part of the graph? Top, good, because I see this 52.6. That's the higher binding energy. Remember, binding energy is that attractive force from the nucleus to the electron. Those positives and negatives attracting. Now, binding energy is also equivalent to ionization energy, which would be the energy needed to be overcome in order to remove the electron. So sometimes you see ionization energy here on the graph, sometimes you see binding energy, and sometimes you just see energy. So this is our 1s. And then if we're following our energies correctly, which would be the 2s? Yes, this 3.04 binding energies are 2s. And then the 1.31, which one is that? What's the next orbital over? The 2p, good. And once again, looking at relative heights, if they didn't give us the numbers here, which they do, but if you look at this peak, it's about double of the other one. And we know that we fill 2 electrons completely in our 1s before we move on to our 2s because of Aufbau principle. So this would be 2s2, and then that would be 2p4. So here's my configuration, 1s2, 2s2, 2p4. That would be my configuration. Now, how do I identify the element again? Periodic table, very good, okay. So 2p4, I just need to look at the end of the configuration. Here is my 2p row, 1, 2, 3, 4. Guess what element we got? Oxygen, very good. So here is oxygen. Identifying the highest gives you your 1s. Now, your turn. Give you a couple minutes. Try to figure out the configuration and the identity. This is also an interesting graph because as you can see on the energies, this one's termed ionization energy on the x-axis, that obviously the scaling for the different orbitals, it becomes a scaling problem. So they use those lines to break up the scales, knowing that there's much higher energy in one area than less as you get further away from the nucleus there. All right, so which peak is my 1s here? The 126, good. Oh, that was not cool. All right, 126 here. Yes, this is definitely my 1s. That's the higher of the ionization energy this time, referring it to there. Then comes the 2s, which would be the next one over. The 2p. What's after the 2p, this last peak over here? The 3s, good. Now, they didn't give us the numbers here, so we have to look at the relative heights. How many electrons in our 1s here? 2, and the 2s. Another 2. As you can see, this 2p is like triple the size of the 2s, so that's 2p6. Multiply that by 3, triple the size. And how many are in our 3s? 2, good, good. All right. This is our configuration. Let's take a look at the periodic table. Which one's 3s? Here's our s block. We go 1, 2. So yes, you found it. It's magnesium. Very good. So there you go. Reading the graph and the electron configuration identity ones, these are the standard problems you'll see. They're not the only ones though that you'll see. So let's look at a multiple choice example where it's not just identifying the element and the configuration. This one's straight from the AP sample questions. So take a moment to read through that. And we're going to look at the multiple choice answers on the next slide. So read through that, take a moment to process. In this particular example, we're only seeing one peak in each element. And they're having us look at the 1s electron. So we're really comparing the 1s electron for both of them. This would be the 1s, this is the 1s, but this is nitrogen. This one's oxygen, comparing two different elements. And it says, which of the following statements best accounts for the peak in the upper spectrum, so the nitrogen spectrum, being to the right, over here, of the peak in the lower spectrum, and where oxygen's is right here. So what are we really comparing here about nitrogen and oxygen and their 1s orbitals? What's different about them? The amount of energy, yeah, the binding energy involved. Which one has the higher binding energy? Yeah, oxygen has the higher binding energy. What does that mean about the attractive force for oxygen? It is stronger, very good. That's exactly right. Now, after we've taken a minute to absorb that, let's take a look at our choices. So here are our choices. Nitrogen atoms have a half-filled p subshell. There are more electron-electron repulsions in oxygen than in nitrogens. Electrons in the p subshell of oxygen provide more shielding than the electrons in the p subshell of nitrogen. Nitrogen atoms have a smaller nuclear charge than the oxygen atoms. Which choice is the best one there when we're thinking about the difference in that binding energy? Very good. Yes, all these stuff about the P's, we're not even looking at the P, we're looking at the S. So here you go, smaller nuclear charge. If you remember, nitrogen on the periodic table has 7 protons. Oxygen has 8 protons. So this part of that Coulomb's law equation we looked at last week, where we were talking about Q1, Q2 over the distance, the R squared. This part is what we're talking about here. The 8 protons gives it a higher magnitude of charge. So that means we get a stronger force for our oxygen. The smaller charge, okay, on the nitrogen being 7 protons, means less attractive force, less amount of positives in there. So that's why that binding energy was lower. So they might give you a question like this where you have to pull in the Coulomb's law. Now this is multiple choice. You don't have to explain it. You just have to understand it and be able to select the correct answer. So let's take a look at this example. Take a moment to read and process that. Any ideas where to start? Find the 1s. I love that idea. That's a great idea. All right. So where do I look to find my 1s? Highest energy. This is 1800. This is obviously the 1s over here. That means B has got to be the 2s. Good. And C is going to be the 2p. Yay. Okay. D, 3s. And then E is the 3p. All right, so now we've identified our orbitals, and we want to know representative binding energy of p orbital electrons. So which ones are our p's? C and E. Don't forget, yeah, we have the 2p and the 3p. So that would be the one that we would want to select here. So in this case, you weren't asked to identify the element or the configuration. You were just asked to identify which ones are the p orbitals. So we would go with C and E because they're both p orbitals. You have the 2p and the 3p. And that's how you would select that answer.